The conflicts between predictions and observations in Big Bang theory are not confined to what is widely known as the crisis in cosmology. Despite the ongoing popularity of this theory, essentially every prediction about the Big Bang theory is increasingly contradicted by ever-improving data. On the other hand, these observations are consistent with a non-expanding universe and the absence of a Big Bang. The real crisis in cosmology is that the Big Bang explosion never actually happened, and time has no starting point, or worse, it never existed. Hawking's perspective on this matter is encapsulated in his statement: "The universe has no clear bang. You can rewind to the earliest moments of existence, but asking what happened before would be like asking why you can keep going north when you reach the North Pole. Time, as we define it, loses meaning as the universe contracts. It never collapses to a single point, but no one has proven that physics operates that way. We always fear the unknown and are startled by the terrifying truths that we misconstrue. After all, what is time? Did the Big Bang happen? Join us in today's video, and don't be shocked when the information we're about to reveal will change your entire perspective on the past and the future. The universe came from nothingness. In 1981, many leading cosmologists from around the world gathered at the Pontifical Academy of Sciences, a landmark at the intersection of science and theology, nestled in an elegant villa within the Vatican Gardens. Stephen Hawking chose the backdrop of August to present what he would later consider his most significant idea, a proposal on how the universe could arise from nothingness. Before Hawking's presentation, all scientific or theological cosmological origin stories provoked the same question: what happened before that? For instance, the Big Bang theory, which was first introduced by the Belgian physicist and Catholic priest Georges Lemaitre, who later served as the president of the Vatican's Academy of Sciences, rewinds the expansion of the universe back to a hot, dense bundle of energy. However, the question remains: where did the initial energy come from? The Big Bang theory faces additional challenges. Physicists understand that an expanding ball of energy would evolve into a chaotic mess, rather than the vast, smooth universe observed by modern astronomers. In 1980, a year before Hawking's speech, cosmologist Alan Guth realized that issues with the Big Bang could be addressed by an additional factor: an initial exponential growth called cosmic inflation, which would make the universe vast, smooth, and flat before gravity had a chance to disrupt it. Inflation quickly became a leading theory for the origin of our universe. However, the problem of initial conditions persists. What is the origin of the tiny patch believed to have inflated into our universe, and what provided the potential energy to inflate it? Stephen Hawking, with his exceptional intelligence, proposed a solution to the never-ending quest to look back in time. He suggested that there is no beginning or end at all. During a Vatican conference, the physicist from Cambridge University, who was 39 years old at the time and still able to speak with his voice, addressed the audience and said, "There must be something truly unique about the universe's boundary conditions, and what could be more unique than the condition that there is no boundary?" The no-boundary proposal, fully presented in a 1983 paper by Hawking and his frequent collaborator James Hartley, envisions the universe in the shape of a sphere. Similar to a sphere with a diameter of 0 at its bottom point and gradually expanding as it goes up, the universe, according to the no-boundary proposal, smoothly expands from a point of 0 size. Hartley and Hawking formulated an equation describing the entire sphere, the wave function of the universe, encompassing the entire past, present, and future simultaneously, prompting contemplation on the seed of creation, the creative force, or any transitions from a time before. In one of his lectures at the Pontifical Academy in 2016, Stephen Hawking stated that the question about what existed before the Big Bang was meaningless. According to the no-boundary proposal, there is no concept of time available to refer to. Hawking compared this to asking what lies south of the South Pole, as both questions are invalid. Hartley and Hawking's proposal fundamentally redefined time. Each moment in the universe becomes a cross-section of the sphere. While we perceive the universe expanding and evolving from one moment to another, real time encompasses the relationships between the size of the universe in each cross-section and other properties, particularly entropy, or its disorder. Entropy increases from the bottleneck to the feather, pointing towards an emerging arrow of time. However, near the bottom of the sphere, the correlations become less reliable. Time no longer exists and is replaced by pure space. As Hartley, a professor at the University of California, Santa Barbara, explained recently over the phone, "We don't have birds in the early universe. Later we have birds. We don't have time in the early universe, but we have time later." Thus, time inherently lacks a starting point, a no-boundary condition version of space-time. Hawking proposed a timeless, boundaryless version. As you approach, the initial timeless state is replaced by imaginary time. In theoretical physics, the Hartley-Hawking state, named after James Hartle and Stephen Hawking, is a proposition related to the state of the universe before the Planck era. Hartley and Hawking suggested that if we could travel backward in time to the universe's origin, we would observe that very close to what could be the beginning, time gives way to space, initially consisting only of space and devoid of time. The inception is entities related to time. Since time did not exist before the Big Bang, the concept of the universe's origin becomes meaningless. According to the Hartley-Hawking proposal, the universe has no conventional origin. It is a singular point in both space and time before the Big Bang. Thus, the Hartley-Hawking state universe has no starting point, but it is not the steady-state universe of Hoyle. It simply lacks an initial boundary in both time and space. The Hartle-Hawking state is the wave function of the universe, a concept used to explore how the universe began, calculated from the Feynman path integral. More precisely, it is a hypothetical vector in the Hilbert space of quantum gravity theory that describes this wave function. It is a function of the metric tensor defined on the compact, D1, dimensional surface, the universe, where D is the space-time dimension. The exact form of the Hartley-Hawking state is the path integral over all d-dimensional geometries with the required boundary conditions on their boundaries. According to the theory, time separates from the three spatial dimensions, as we know it today, needs clarification. After the universe reaches the Planck age, a wave function of the universe like this can be shown to satisfy the Wheeler-DeWitt equation. Imaginary time is a mathematical representation of time appearing in some approaches to both special relativity and quantum mechanics. It finds applications in bridging quantum mechanics with statistical mechanics and in some cosmological theories. Mathematically, imaginary time is the real time that has undergone a Wick rotation, where its coordinate is multiplied by the imaginary unit I. Imaginary time is not imaginary in the sense of being unreal or fictitious, like challenging the logic of irrational numbers, but rather it is simply expressed in a form known as imaginary numbers by mathematicians. People might think this means imaginary numbers are just a mathematical game unrelated to the real world. However, from the perspective of empirical philosophy, one cannot definitively determine what is real. All we can do is find mathematical models that describe the universe we inhabit. It turns out that a mathematical model involving imaginary time predicts not only the effects we have observed but also effects we cannot measure yet but still have faith in for various reasons. So, what is real and what is imaginary? Is the difference only in our minds? In the theory of relativity, time is multiplied by I. This can be accepted as a characteristic of the relationship between space and time, or it can be incorporated into time itself as imaginary time, with the equations rewritten accordingly. In the physics of cosmology, imaginary time can be integrated into certain models of the universe, solutions to the equations of general relativity. Specifically, imaginary time can help smooth out singularities, where known laws of physics break down to eliminate these singularities and avoid such breakdowns. For example, the Big Bang appears as a singularity in ordinary time, but when modeled with imaginary time, that singularity can be removed, and the Big Bang operates like any other point in four-dimensional space-time. Before the Big Bang, there was nothing but an ocean of energy and time as well. It did not exist. The scientific evidence against the Big Bang. The debate over the issue of imaginary time among scientists ultimately returns to the fundamental question of the validity of the Big Bang. Since the launch of the James Webb Space Telescope in 2021, increasing evidence has been challenging the vagueness and gaps in this century's theory. Firstly, the emergence of light elements, lithium and helium. The Big Bang theory predicts that a certain amount of light elements, including lithium, helium, and deuterium, must have been created in the explosion believed to have formed the universe. For lithium, the prediction is 400 lithium atoms for every billion hydrogen atoms. However, astronomers have measured the abundance of lithium in old stars in our galaxy and found that the Big Bang prediction is not accurate. They know that stars formed very early in our galaxy's history because they contain a very small amount of iron and other heavy elements produced by pre-existing stars. In most of these stars, the abundance of lithium is only 160 lithium atoms per billion atoms, much lower than the Big Bang prediction. Moreover, with more data accumulated over the past few years, it's evident that older stars have less lithium. A recent study by Lerner, presented at the January 2020 meeting of the American Astronomical Society, indicated that observations of the abundance of both lithium and helium in current old stars deviate from predictions by over a dozen standard deviations, and the gap is widening at an accelerating rate. The oldest stars have less than half the amount of helium and less than a tenth of the amount of lithium, compared to the predictions of the Big Bang nucleosynthesis theory. The lowest observed lithium level is below 1% of the theoretical prediction. Indeed, the most consistent evidence is that neither helium nor lithium was formed before the first stars in our galaxy. Equally important is the research indicating that the observed abundance of these light elements has been predicted through an alternative explanation, proposing that these elements were created by stars in the earliest stages of the galaxy's evolution. This alternative explanation, referred to as the galaxy origin of light elements, or the Golay hypothesis by Lerner, stems from theoretical expectations that the first generation of stars formed in a galaxy would be of average mass, heavier by 4 to 12 times that of the Sun. These stars burn hydrogen into helium in tens to hundreds of millions of years, much faster than our Sun's burning rate of 10 billion years. The helium is then dispersed by powerful stellar winds in the final stages of these stars' life cycles. Cosmic rays from these primordial stars, colliding at high energies with other nuclei, create deuterium and lithium. Although this data entirely contradicts predictions about the Big Bang, they have been predicted and explained simply by theories of galactic evolution that exclude the Big Bang, including a paper published by Lerner in 1989. As known, lithium is created by cosmic rays emitted from early stars colliding with carbon and oxygen nuclei, as well as by stars in their giant phase. Lerner shows that similar stellar processes can account for the observed abundance of helium from nuclear reactions in early primitive stars and deuterium. The recent study, incorporating new calculations based on the GOL hypothesis, demonstrates that early stars not only produce the observed amounts of helium, deuterium, and lithium, but also generate other elements such as carbon, boron, and beryllium with observed quantities in the oldest stars. Lerner explains, The goal hypothesis was first published in full in my paper in 1989 and has been discussed by others before that. The predictions made in that published paper have been confirmed over many decades of subsequent observations. Unlike the predictions of the Big Bang hypotheses, the new work I am reporting at this conference makes the predictions more accurate and based on much broader knowledge that we currently have about the evolution of stars. These conclusions, based on observations of old stars in our galaxy, are reinforced by recent observations of conditions in newly forming galaxies. These galaxies are extremely bright, converting hydrogen into helium at rates hundreds of times faster than our current galaxy. Research from other scientists published last year showed that their brightness is controlled by stars with masses around 8 times the mass of the Sun, as predicted by the goal hypothesis. Structures too large to form in the time since the hypothesized Big Bang. The Big Bang theory proposes that the universe originated with an almost entirely homogeneous distribution of matter, uniform, and structures gradually formed from stars to galaxies and then conglomerated into superclusters. However, increasingly larger structures have been discovered earlier than expected. For example, in 2013, a group of observers, led by Roger Close, found a colossal collection of quasars spanning over 3 billion light-years, existing billions of years before. According to their perspective, it is too large to be created within the framework of conventional cosmology. Even larger galaxy structures were found in 2016 by Hirikoff and colleagues. Indeed, Lerner pointed out that, considering the current low velocities of galaxies, the large-scale structures of galaxy clusters that we observe would take hundreds of billions of years to form. In groundbreaking work in 1986, Lerner used plasma physics to predict the fractal structure of the universe, including structures with diameters of up to billions of light-years and structures discovered later. According to Lerner's theory, these structures could only form in a universe with a history stretching back more than 14 billion years. Another piece of evidence casting doubt among scientists is dark matter. The Big Bang theory predicts that most of the matter in the universe is dark matter, unlike any matter found on Earth. Increasingly sensitive experiments on Earth have failed to provide any conclusive evidence for the dark matter particles predicted by the Big Bang theory. Additionally, astronomical evidence has also ruled out dark matter. The simplest evidence is the relatively low speeds of galaxies in the universe. The large amount of dark matter predicted by the Big Bang would create gravitational forces that could cause galaxies to rotate at speeds of hundreds of km. However, the observed average speed is 50 km, eliminating the large amount of dark matter required for the Big Bang, as shown by Barishev, Silos Labini, Montuori, Pietronero, and Teiricurpi. The ultra-fine distribution of dark matter needed to avoid high speeds is also incompatible with the clumpiness, inhomogeneity, of observed matter at all scales. Furthermore, the satellite galaxies of both the Milky Way and the nearby Andromeda Galaxy have disk-shaped configurations, as expected if gravity arises from ordinary matter. If gravity arose from dark matter, the satellites would have to be in a random sphere. This evidence is entirely inconsistent with the dark matter hypotheses, as demonstrated by Pavel Krupa and many other researchers. Perhaps most decisively, Ohm and Krupa in 2018 pointed out that the unavoidable effect of viscosity with dark matter would cause galaxy groups to merge quickly to a level that very few could observe, contrary to the existence of many such groups. Once again, there are simpler alternatives, not involving the Big Bang, to explain the data. Over 30 years ago, Peratt and Green demonstrated that electric forces would create constant rotation speeds in spiral galaxies, long used as the key evidence for dark matter. These speeds are measurements of the velocity of anisotropic plasma emitted in a galaxy, influenced more by electrical forces than gravitational forces. Jolacha, Bratek, and others have shown that in the outer regions of galaxies, including the Milky Way, the gas moves faster than the stars, and this difference can be explained by the influence of magnetic fields on the gas. More recently, Konkel and Covey provided persuasive evidence of the magnetic field's influence on the motion of stars. They discovered that a significant portion of stars nearby is embedded in filaments with lifetimes of hundreds of even GY. Although the authors did not draw this conclusion in their paper, it is clear that gravity alone cannot create long-lasting filamentary structures. However, magnetic fields with observed intensity can control the dynamics of dense gas filaments. And these filaments can, in turn, control the gravitational motion of stars within them. Magnetic fields, instead of assumed dark matter, can provide additional observable forces in galaxies. Surface brightness. The hypothesis that the expanding universe is the fundamental pillar of the Big Bang theory has faced challenges. Observations of the sizes and brightness of thousands of galaxies contradict predictions based on the expanding universe hypothesis, leading to a significant shakeup of this crucial pillar, as detailed in a paper in the monthly notices of the Royal Astronomical Society by lead scientist LBP Fusion Eric Lerner, titled Observations Inconsistent with Predictions of Galaxy Size and Surface Brightness Growth Based on the Expanding Universe Hypothesis. The study revealed that no predictions about the universe's expansion published regarding the growth of galaxy sizes align with actual data. All proposed physical mechanisms for galaxy development, such as galaxy mergers, also conflict with observations. However, the paper notes that the data align well with the contrary hypothesis that the universe is not expanding, and the red shift of light is caused by a different, currently unclear process. This research tests a prominent prediction from the 1930s regarding the Big Bang hypothesis, suggesting that objects at very distant distances should appear larger rather than smaller. According to the hypothesis, this is due to optical illusions caused by galaxies much closer emitting their light. This prediction was reiterated throughout the 1980s, but by the 1990s, the Hubble Space Telescope did not confirm that prediction. Instead, Hubble's images showed that the farthest galaxies appear smaller in reality. Subsequently, a group of researchers proposed an additional hypothesis that galaxies indeed grow in size over time. Therefore, very distant galaxies, when observed from billions of years ago, were theoretically much smaller than galaxies today. This way, the intrinsic sizes of galaxies in the 1990s, based on the developing galaxy theory, completely debunked the optical illusion predictions from the 1930s. In Lerner's paper, the quantified predictions from developing galaxy theories were tested based on the observed sizes of thousands of spiral and elliptical galaxies, using HST observations from 2004 to 2014. The paper limited the samples to galaxies with similar near-ultraviolet brightness. The observed data did not closely match predictions that galaxy sizes increase proportionally to the rate of universe expansion. Furthermore, Lerner pointed out that the process hypothesized for the development of elliptical galaxies, the merging with other galaxies, occurs at a rate almost 10 times slower than the growth rate proposed in the hypothesis. An even more severe inconsistency arises when comparing the gravitational mass of distant galaxies, calculated from their rotation speed and size, with the mass of the stars within them, calculated from their emitted light. Predictions about size based on the expanding universe theory lead to a gravitational mass smaller than the mass of the stars, which is inherently impossible. While predictions about the expanding universe do not align with the data, Lerner notes that predictions based on a non-expanding universe fit both spiral and elliptical galaxies at all distances, with an accuracy of a few %. Regardless of the distance, in a non-expanding universe, galaxies with a certain brightness have the same size, just as predicted by the non-expanding universe hypothesis. Lerner explains, in this hypothesis, The simple linear relationship between the redshift of light and distance is due to something happening to light as it travels, not the expansion of space. Currently, no one knows what could cause this, but the linear relationship and the non-expanding space make predictions that align with the data, whereas predictions about an expanding universe do not. The Big Bang theory has several issues that its supporters dismiss as anomalies. However, these issues contradict all the theory's predictions. To address this, supporters of the theory keep adding parameters to account for new data that doesn't fit. This has resulted in over 20 parameters being adjusted, and the theory cannot predict new results, which is a hallmark of a sound scientific theory. Recent results from the biceps instrument have led researchers to add even more parameters to the theory to explain contradictions between biceps and Planck results. On the other hand, hypotheses that align with a universe that had no beginning in time and no Big Bang can explain the data that contradicts the Big Bang theory in a much simpler way.